All right, so this is the 2023-2024 test for honors. I believe this is slot 3. Unfortunately, it's drawing in white, which is not very helpful. So we'll go ahead and say that this is 3H, and we'll pick a little finer pencil. Okay, so anyway, I'm going to apologize. I'm a little sick as I write this. It's Saturday night at, I don't know, 7-ish or something, 7:30, and I got a COVID shot yesterday, so I'm feeling the effects of that. Anyway, so here we got car A and we got car B. We have two cars. Car A is moving at 15 meters per second, so V naught A is 15 meters per second, with an acceleration A sub A of 11 meters per second squared. A sub A is 11 meters per second squared. Car B is moving with a velocity of, let's see, V naught B of 32 meters per second, and an acceleration of AB, A sub B, equals negative 12 meters per second squared. Okay, the cars are initially at rest and separated by a distance of 1.5 kilometers, okay, so 1,500 meters on the x-axis. Okay, so that tells us, and this was the big trick to this problem, is that x naught B and x naught A, so A is at a position, we'll call it 0, and B is at a position 1,500 meters, okay? It could have been any x naught A or x naught B as long as they were 1,500 meters apart. Okay, so most of you got, well, I'll talk about the grading later. Okay, this is a tough problem, partial, okay. At what time in seconds do the cars meet? Okay, so we need time. Okay, that's for both cars to have the same x, for XA to equal XB. Okay, so that means we need an equation for XA and XB that involves, that has time in it, right? Because that's what this is all about. Okay, so for A, the equation for A is XA equals X naught A plus V naught AT plus 1/2 AAT squared. Okay, same equation for B, XB equals X naught B plus V naught B T plus 1/2 ABT squared. Okay, so same equation of both of them. We're just going to plug in different numbers. Okay, so for XA, so XA equals 0 plus 15 meters per second times T plus 1/2. That acceleration is 11 meters per second squared. We want to kind of make sure that we get our 2's looking like 2's. T squared and XB equals 1,500 meters plus V naught B, which is 32 meters per second, times T plus 1/2 times negative 12 meters per second squared. Oh, I forgot time. Sorry. Okay, that's exactly the sort of error that some of you guys did. Not a huge loss for little careless errors like that. Okay, so what we're looking for is we're looking for a time when XA equals XB. So that means I can say that XA and XB are the same thing. Okay, so if I set them equal to each other, I'm going to get 15 meters per second times T plus 1/2 times 11 meters per second squared, T squared, equals, okay, so I'm going to set that equal to XB, 1,500 meters plus 32 meters per second times T plus, I'd like to just go ahead and divide by 2, but I'll leave it like this for one more step. You know what? Let's do it right now. Let's do it here as well. Let's make this 5.5, 5.5 meters per second. And this is 1/2 of negative 12, so we will make that negative 6 meters per second squared times T squared. Okay, cool. So now all we need to do is solve this, and this is it's a quadratic. It just takes a little bit of, combining terms and whatnot. Let's see here. So if I take this negative 6 and put it over here, that gives me 11.5 meters per second squared, okay, times T squared. Take this 32 and subtract it off of that side, and I'll get a plus a negative 17 meters per second times that T. And then I'll bring this 1,500 over to the other side too, minus 1,500 meters equals 0. Okay, so now this is a nice, pretty quadratic formula. So I can say, okay, t equals negative b, which is negative 17 meters per second, plus or minus the square root of b squared. I'm not going to bother with that negative sign because it's going to get squared out. Minus 4a is 11.5 meters per second squared. C, negative 1,500 meters. Okay, all divided by 2a, so 2 times 11.5 meters per second squared. And of course, if you'd had a stronger calculator with you, it would be nice because you could just use the stronger calculator to solve this for you. You do not have a stronger calculator. I do not either. So 17 meters per second plus or minus, or at least I didn't when I created this key. The square root of, well, I guess we're not going to have a square root here. Looks like we're just going to figure out what this thing is. So it's a 263.23 meters per second. Remember, I'm trying to keep extra sig figs. I know basically, I think I'm going to end up with 3 here. Yeah, because I've got 3 right here. No, I've got 2 in most of this problem. So I'm going to end up with 2 in the final answer. Okay, and then I'm going to divide that by 23 meters per second squared. I can't tell you how many times I solved this, where for some reason I did 2 times 11.5 and I put 33. And I was beating my head against, it wasn't very good. Anyway, so this will give us 2 solutions, negative 10.706 seconds and 12.184 seconds. And since I started this whole problem at t equals 0, therefore this is the answer for the time. Okay, so now I want to get, let's see, so if we go up here, then it says, what is the displacement in meters of car A and then car B when they meet? I think, now that I'm thinking about this, I think some of you guys, me included maybe, forgot that bit about the meters and put it in kilometers. I know I put it in kilometers, at least one of them. Anyway, so delta XA equals, basically this is the exact same equation, except what I'm looking for now is delta X, so I'm combining those two into X minus X naught. So delta XA, and then the right-hand side of that is all of this. So we're going to get 15 meters per second times t plus 1/2 a. Oh, sorry, not a. Well, it could be a, but let's actually let's use the actual value. So 11 meters per second squared, and then we're going to plug in 12.184 seconds squared. Okay, so delta XA. If we plug that into our calculator, we'll get 999.23 meters. Cool. Okay, so then we'll do delta XB. I think there was only one person in this class who decided that, well, if we know this is 993.9, and we know that the total distance between them was 1,500, then we know that this one is going to have to be negative 500.77. Only one person did that. Most of you guys did not do that. Anyway, let me erase that. It didn't occur to me to do it that way either. It seemed almost like a cheap trick or something. Although it's perfectly logical, so I will accept that. So we'll get plus 1/2 times negative 12 meters per second times. Well, this is horrible. Let's go into blue. 12.184 seconds squared. Okay, so delta XB, if you plug all that into your calculator, you'll get negative 500.81 meters. So we're feeling pretty good about that, right? The B car came backwards 501 meters, and the A car went forward 999 meters. However, we need 2 sig figs here. So delta XA is basically 1.0 times 10 to the third meters. Okay, and delta XB is negative 5.0 times 10 squared meters. Some of you guys did something I've never seen before. You put a little line over the top of your last sig fig. So I'm gonna have to ask you guys about that because I've never seen that before. Okay, so that's how we do it. Oh wait, we need to report our time as well. Time, we need 2 sig figs, so this is gonna be 12 seconds. Okay, cool. All right, so that's the problem there. It's a lovely problem. The way to think about this problem, by the way, this is the flagpole problem. You remember the flagpole problem where we had 2 runners? and you had a runner over here, and he was running, I don't know, this way, and then we had a runner over here, right? And he was running that way, and he gave me the initial position for this one, and we gave the initial position for this one, and we gave a velocity. The only difference here is we had acceleration. So I expected y'all to, do okay on this, and I'd say a third to a half of you just ate this thing for lunch. Most of you guys had a little error here and there, which is completely to be understood. There's kind of a lot going on here. Plus, anytime you have a quadratic formula, the room for error gets pretty big. All right, so we'll go down here, and we'll do the 1D velocity versus time graph. I'm going to have to draw it real quick. Okay, so let's see. So this is V in meters per second. And we had a nice little line that looked kind of like this. All right, so I'm tired of drawing, so we're just going to go ahead and solve the first one. Okay, so the first thing that they told us, I don't have it in this particular version, but on yours it said the initial position was at x naught equals -5 meters. So, so you got to, figure out where that is. I don't really understand why a lot of you did not want to draw your axes. Like, I didn't draw the axis for you so that you could move it where it made sense to you, and then a lot of you were like, I'm not going to draw it. I accepted that, but please be a little bit more reasonable in the future. All right, so anyway, so we're going to start right here at x equals -5 meters. It's also really helpful to, label your points. If your labels were good, I mean, if your points were directly where they needed to be and I could tell exactly what you were going for, I accepted you not doing that. I'm not really a huge fan of that, though. You should really, it should be a habit by now. Okay, so the area within this first rectangle right here. So let's go ahead and get our areas. This particular area is, let's see, what is that? That's 3 by 2, so this is a +6 meters. Okay, I'll just go ahead and box these areas. Okay, this particular is a combined area, right? We've got some positive and some negative, but the average velocity is +2 meters per second plus -1 meters per second, right? So that's this value right here and this value right here. Okay, we're going to make that an average by dividing by 2. And then we're going to multiply that by the time over which this is happening, which is 1 second. Okay, so that's delta x. Okay, so basically delta x equals v bar times t. Okay, so if we do that, we'll get that combined delta x of of 1/2 of a meter. Okay, so that tells me, how much I'm going to change over that 1 second. And then this last little rectangle here, okay, so it's got a height of 1, or really a -1, and it's got a width of 2, so we're going to have a -2 meters right there. Okay, cool. So now we're going to go up here, and let's see what we can do. So we started at -5 right here, and we're going to go up 6. So right here, we're going to end up at a +1. Okay, this is where it gets a little tricky, right? Especially because I didn't leave myself a whole lot of space. So -1, -2, -3, -5, and this is 1, 2. Okay, so note that this is a constant value. So this one's going to have a constant slope. Okay, meaning it's going to be a straight line. Okay. Ooh, my license is not quite long enough to make that. Maybe if I zoom out. Aha! Now my license is long enough. Aha. Okay, so that's a straight line. It's not perfect. Drawing on iPads is a little bit weird. Okay, so now we are going to, this total delta t is -1/2. So when we were here, we were at 1, 1 second, 1 meter. So now we're going to go up another half meter. So we're going to end up at about, I don't know, like right there. Okay, and this is one of those things where I don't really understand why you guys didn't want to label your points. Some of you lost points because I couldn't tell where your points were. Anyway, so there you go. Okay, now I will note that it kept going up. Let's see, I think I can get this with maybe this ruler. It keeps going up until this point right here, right? Because we have all that positive area. Okay, and then it's going to come back down. Okay, so it's going to go up and it's going to peak here and it's going to come back down. Okay, that point right there, we'll figure out that point in a second. That was a bonus. If you got it, then good for you. Okay, most people did not get that. Okay, so then we're going to go down another 2 meters over the next 2 seconds. So we're at 1.5 and we're going to end up at -0.5. So we're at 1.5, we're going to go down to -0.5, which is about right there. Okay, so this will be 6 seconds, -1.5, nope, -0.5, excuse me, -0.5 meters. Okay, and we'll notice again, we've got a constant value. So we're going to have a constant slope from there to there. So constant slope. Okay, which means I just pull out my license again and make the line pretty. Okay, the fact that this is as kinked as it is kind of gives me the idea that this point is probably too high. But let's go ahead and figure that out. So if I want to know where this thing crosses right there, basically I'm looking for the time from 3 to, whatever, 3.5, 3 2/3, 3 3/4, whatever it might be. And so I note that this line has an equation, right? And so I'm going to say that V equals V naught plus AT, okay? And so I want to know what the time is, okay? So this is what I'm looking for when this is 0 meters per second, right? So that's when I'm crossing this line right here. Okay, so I'm going to say 0 equals the initial velocity is right here, 2 meters per second, plus A. So acceleration is the slope of that line. We got to get this anyway. So the slope of that line, I wonder how they came up with M for that. But anyway, the slope of that line is we went down 3/1. So it's -3 meters per second squared. We needed that number anyway for the part when we go down low. So -3 meters per second squared. And then here's my time. So if I solve that, T equals, what is that? 2 divided by -3. So what the? No, right, because you move it over to the side, so it's positive. 2/3 of a second. Okay, so that's this time right here. That's 2/3 of a second. Okay, so 2/3 of a second, so this is 3 2/3 of a second. Okay, and what's that height? Well, we need to figure out what the area of this particular triangle is. Okay, and that's not so hard once you know the base, right? So the base, this is 2/3. The height is 2. Okay, so 2/3 times 2 is 4/3, divided by 2 is 2/3. So in other words, the change in position is we're going to go up 2/3 from this 1 right here. We're going to go up to 1 2/3 of a meter. Okay, so there you go. Okay, and that's how we would solve this particular, that particular portion of the problem. Okay, so anyway, so now that we're here, let me go ahead and get my slopes. Let me put them in like green or something so that they'll pop. Okay, I already got this slope. M equals -3 meters per second squared. Slope here is 0. Slope here is 0. Okay, so this is a pretty easy graph down here. Let's see here. Okay, that doesn't look so terrible. So this is acceleration in meters per second squared. And basically all of our values, we've got a value of 0, we've got a value of 0, we've got a value of -3. Okay, so basically 1, 2, 3, 4, 5, 6. The only interesting thing is happening from 3 to 4 seconds where I have a value of -3. And the cool thing about this particular graph is, you don't really have to do very much, right? Okay, some of you put open circles here, which is almost certainly a better way to do it than I'm doing it. So, you could put like dotted lines here. I'm not really going to get too worried about that. However, this did need to be -3 over here, -2 and -1. Okay, obviously those are not very well drawn tick marks, but anyway, so that's how you do it. When grading this, what I did, so this one was worth 7 points. And all I did was, you got that point right, you get a +1. You get that shape right, you got a +1. You got this point right, you got a +1. You get this point right, you got a +1. You got this shape right, you got a +1. You got this shape right, you got a +1. You got this shape right, you got a +1. A lot of you guys are going to see a lot of OKs on your thing where I circle the point and I write OK. And usually if I did that, that meant that this number was correct if the previous point had been correct. But usually it meant that you made a mistake on the previous one. Okay, so I was trying not to double count for that. Okay, this one was worth 5 points. There really wasn't much to grade here. Most of you guys did really well overall on this particular part of the assignment. So I was very happy with your work here. I forgot to say up here, so the way I graded this, so this and that's worth 4. This was the big kicker right here. That's worth another 2. And then this work here, if you just somehow set your displacements equal to, or your positions equal to each other, then I could have given you points in here, right? If you made an algebra error, like if you set this particular equation, like if you got this equation right here, and a lot of you did, and then you didn't even write all this out, but you got this equation right here, then that's essentially a 10-pointer right there. Okay, I mean, not getting the answer means there's a -1 in there, because you flubbed the algebra. But let's be honest, the algebra is tricky. And then down here, this was +5, and this was +5. Okay, so a lot of you guys did some little weird things where you solved for xb and xa instead of the delta xa and delta xb, and so that lost you a point. A lot of you guys didn't know what the time was, so you just said I'm gonna assume 5 seconds for these times. Oh, it looks like I forgot to write in that 12.184 right there. I apologize for that. Okay. Anyway, same grading technique for the second test. Okay, so let's do this second test, and then I will lay down and let my head recover. All right, so I guess we would call this a key. I always feel so arrogant calling it the key. I guess that is my job, so what can I do? What can I do? Okay, this is a very, very similar test. I'm kind of questioning whether or not why I'm solving this one again. But I guess, if it's useful to you, it doesn't cost me anything to just put it up there. There is a third test here, so if you're curious and you want to see what the makeup was, we'll go ahead and do that too. So we got XA equals XB equals, I'm going to kind of skip some steps here just because I can. So the XA, it starts at 0 meters. Okay, so this is all coming out of x equals x naught plus v naught t plus 1/2 a t squared. Okay, so the initial position for B is, well, it's 2300 if I can remember how to draw. Okay, and then we're going to go plus. Now we're going to go over the v naught t. So the v naught is, for A, it's 15 meters per second. 15 meters per second. Okay, times t. For B, it is -23 meters per second times t. A really wonderful question would be to ask, what's the closest they ever get to each other if I had them not actually, I think you would need calculus for that. But anyway, and then acceleration A, so now we're going to go to this term, plus 1/2, acceleration of A is 11 meters per second squared times t squared, and xb is going to be -12 meters per second. So, I forgot my 1/2. 1/2, 12 meters per second squared times t squared. Okay, cool. So there you go. Just like the last one, I apologize, I'm not doing all the little intermediate steps. So again, we're looking for the time when XA equals XB. So we'll go ahead and set them equal to each other. So 15 meters per second times t plus, I'll go ahead and do the little bit of math here, 5.5 meters per second squared times t squared equals 2300 meters. Do I want to do minus? I like to put my negatives in there because it helps me when I'm doing the quadratic formula. T squared, is that plus or minus? Is that a -12? Oh yeah, that is a -12, so I forgot my minus right here. So, and I put a squared right here. Okay, t plus -6 meters per second squared times t squared. Okay, so again, we're going to rearrange this just like the last one. Let's see, so the t squareds, let's bring this over here. So I've got 11.5 meters per second squared. Bring this one over. So that's 38 plus 38 meters per second times t. And then I'll bring this one over, which will become negative 2,300 meters equals 0. I guess usually I would do a plus a negative like that, just because it helps me with doing the quadratic equations, because we've got a nice little quadratic here. So let's go ahead and solve this. So we will go ahead and say t equals, let's see here, negative b, negative 38 meters per second, plus or minus the square root of b squared, 38 meters per second squared minus 4a is 11.5 meters per second squared times c, which is negative 2,300 meters. Okay, all divided by 2 times 11.5 meters per second squared. Okay, one of the interesting things here before I continue, and I wish I had pointed this out earlier, is to note that even the quadratic formula works with units. Okay, so, we've got meters per second squared here, and we're going to end up with meters per second squared there. And when we take the square root, we're going to get meters per second. So all along the numerator, we're going to end up with meters per second. We're going to meters per second divided by meters per second squared on the bottom, and so we're going to get seconds. Okay, so we end up with t equals negative 38 meters per second plus or minus 327.48, keeping way too many sig figs so that we don't have a rounding error, all divided by 2a, which is going to be 23 meters per second squared. By the way, it is rare for my tests to be this similar. I mean, you're always, I know you're going to probably talk to each other, but I would request or suggest that it's not a good idea to rely upon it. Okay, negative 15.890 seconds and 12.586 seconds. Okay, so because I started this problem at t equals 0, it is the positive root that we want. So it's going to be 12.586 seconds. Okay, so now the second thing I wanted, what is the displacement in meters of car A and car B when they meet? I was thinking about asking, what is their speed when they meet? That would be interesting. Not even really a different problem, but a little bit easier calculation, right? So you just do V equals V naught plus AT. All right, so anyway, so now we're going to basically do this equation right here, but I'm not worried about the initial condition for either of these, right? All I want to know is how far did they travel. Okay, so delta x A equals 15 meters per second times t plus 1/2 times 11 meters per second squared times t squared. Okay, so I'm going to plug in that value for time. So delta xa equals 15 meters per second times 12.586 seconds plus 1/2 times 11 meters per second squared times 12.586 seconds squared. Delta xa. Okay, so if you plug that into your trusty dusty calculator, which I highly recommend, you get 1060.0 meters. Okay, way too many sig figs. So we'll just leave it like that for now. And then we'll do the same thing for B. Looks like I got to kind of work below here because I ran out of space. So delta xB is negative 23 meters per second times t plus 1/2 of negative 12 meters per second squared times t squared. So delta xB equals, let's see here, negative 23 meters per second times 12.586 seconds plus 1/2. Okay. T squared is 12.586 seconds squared. Delta xB equals, okay, negative 1239.9 meters. So we have to feel pretty good about that. Okay, because clearly, one car went forward 1060, the other one has to come back 1240. Okay, so we need two sig figs in our answers. So we would go ahead and say, well, t equals 13 seconds. Boom. Delta xa equals, well, they wanted, technically they wanted meters. I say they, I wrote the problem. I guess I did steal it and adjust it. So anyway, so 1.1 times 10 to the third meters. To me, this is really why we have kilometers, is so that I can just say 1.1 kilometers. Anyway, delta XB equals negative 1.2 times 10 to the third meters. Okay, cool. All right. Yeah, I don't think there's any real interesting points here that I didn't address already when I did the first half. Okay, so it looks like we got another one of these, and again, I'm going to have to draw it. All right, so let me give this a V in meters per second. All right. Okay, let's start by calculating some areas. So the area of this little box here, we zoom all the way in, it's a 1 by 1, so we're going to get -1 meter. Okay, the combined area of these two triangles. Let's see here. So we want to know delta x equals v naught t. So delta x equals the average velocity, which was what, a -1 and a +2. So -1 meters per second plus 2 meters per second divided by 2 times the time, which was 2 seconds. So I believe that combined total area is delta x is 1 meter. Okay. And then over here for this big rectangle here, I believe we have a height of 2 and we are 3 wide. So this is going to be a +6 meters. Okay, for this whole area here. Okay. All right. So now that we have that, oh, I haven't drawn my other axis yet. Let's do that. Okay, so let's go ahead and begin this. We're going to use our trusty dusty black. I'm going to use it fairly thick so it will show up. And of course, the one thing that is not on here is that I wanted you to start. I gave you x naught equals -5. Why won't you draw it there? Come on, get out of here. Okay, sorry, we had a little snafu there. What, son of a monkey's uncle. Okay, so x naught equals -5. Dadgummit. Is it really that hard to just say x naught equals -5? Come on, you punk. All right, there you go. So that's where we're starting. Okay, so here's -5, so that's where we're starting. That's your first point. You get 1 point for doing that. All right, now we're going to go down here, and we know that we're going to go down by 1. So we're going to end up down here. Okay, let's assume that my drawing is a little bit better. Okay, so I went down 1, so now I'm at 1 second, -6 meters. Okay. We've got a constant value here, so we will have a constant slope up here, so this will be a straight line. Okay, and then from here to here, again, ignore my horrible drawings. Next time I really need to scan in the graph paper. Anyway, so we know we're going to go up 1 meter, so I'm going to end up at, let's see here, -5. So it's going to be 3 seconds, -5 meters. Okay, and we'll note that this is where things are going to quote unquote peak, or the inverse of peak. They're going to trough, right? Now we don't know what that value is yet, but we know that this thing is going to be smiling this whole time. Okay, with a peak right here. And we'll go ahead, we'll figure that peak out later. You can put a little dot here to let me know that, you intend that to be curved. Okay, so at this point, we're going to go up 6 meters here. And so as we go up 6, oh wait, how did I know that this was curving? How did I know that this was smiling? Okay, so this slope was, it had a negative value, so we had a negative slope right here. We had a 0 value here, so we had a 0 slope right there. So that kind of lends into this, right? Negative value into flat. And now we've got a slope of 0 here coming out of there, and we're going to a positive slope here, so we're going to kind of smile up like that. The other way to do it is just calculate the slope of that line. If it's positive, it's smiling. The slope of that line is positive, so it is smiling. Okay, so now we're at -5, and we're going to go up by 6. So we're going to go up to -2, like right there. Excuse me, -1. So that's going to be 6 seconds, +1 meters. Okay, and I don't know if my license is going to quite be long enough. So let's zoom out a little bit so that my license will be long enough. Boom. Okay. Cool. So just like with the other class, the way I graded it was this point was worth 1, this point was worth 1, this shape was worth 1, this shape was worth 1, this point was worth 1, this shape was worth 1, and this point was worth 1. Obviously, you can screw up pretty early, and it will cascade through. So if you did that, all the ones afterwards, which had the correct changes based on these numbers, you got like a little okay by it. Okay, so the last thing I want to do is I want to go ahead and get this point, which was kind of an unwritten bonus. A lot of you went ahead and got it, and that was cool. So what we would do to get that particular point is we want to work with the equation of this line. And so I would say, well, V equals V naught plus AT. How do I know that this is the equation that I'm working with? Well, because I'm on the V graph, okay, for some reason. Here we go. Let's see, because I'm on this graph, right? So if I'm on that graph, this is the slope of that graph, y equals mx plus b. Here's my b, here's my m, here's my x, right? That's how I know. All right, so anyway, so v equals v naught plus at, so I'm going to go for this little interval right here. Okay, so I want to know what the time is when the v is 0. So 0 equals v naught. I'm going to start right here. -1 meters per second plus the acceleration. Oh, that's the slope of that line. What is the slope of that line? Let's see. We went up 1, 2, 3. We went over 1, 2. Oh, we went over 2. So 3 halves. So this will be 3 halves of a meter per second squared. Okay, and then here's my time. So if I resolve this around, I think I'm going to get, what, 2/3? +1 multiplied 2/3 of a second. Okay, so that's measured from where I started this particular little problem. So this is 2/3 of a second right here. Okay, which means from here to here is 4/3 of a second. Not that I really care all that much about that. I mean, I can use it to test, to check, right? Because I could do this area and see if it lines up. But anyway, so I've got this width of 2/3. I've got this height of 1. So 1 times 2/3 is 2/3 divided by 2. And so this is an area of 1/3 of a meter. Okay, so, and that is a -1/3 of a meter. So if I started here at -6, I will end up at -6 1/3 of a meter. And my time is 1 second plus that 2/3. So this will be 1 2/3 of a second. Okay, so this is, that was just a little, if you did that, great, cool, +2 or +1 for each of those values. Okay, so now we need to get the acceleration. Look at the acceleration is not so bad. I'm starting to feel a little better. Maybe teaching is the antidote to COVID shots. Anyway, hope you guys are having a better weekend than I am. But look, it's okay. Nothing really terrible happened. I just got a COVID shot. I also got a flu shot because you all terrified me with all your flus and your breathing everywhere, All right, so here we go. So here's our time in seconds. And then we've got a 1, we've got a 2, we've got a 3. Obviously, I'm eyeballing this, so bear with me. It's not going to be that good. But in this case, it's totally okay. I mean, it was not really going to matter all that much because, this is acceleration in meters per second squared. And basically, we're just going to plot the slopes up here. So the slope, this has 0 meters per second squared. This has 0 meters per second squared. Well, that has 0 meters per second squared. And the slope of this particular line, we calculated right here to be 3 halves of a meter per second squared. Okay, so I'm going to go ahead and erase all this because it's in the way of my drawing. Okay, so when this thing is done freezing, this will be 1, this will be 2, this will be -1, this will be -2. By the way, I got to say this. Some of you guys did the strangest intervals. Some of you guys were like, well, this is like 1.25 and this is 2.5. I don't have no idea why you did that. It was really hard to follow along with. I'm not being that critical because I've done things a lot worse, especially when I was a student. So we got 0 meters per second for the first second. We got, looks like we got 0 meters per second for the last 3 seconds. Okay, and then we've got positive, what was this? Positive 3 halves? Dadgummit. I erased it. What was it? Okay, let's see. We went up 1, 2, 3 over 2 seconds. Yes, 3 halves. Okay, so this is going to be 3 halves. And I'll do it the way a lot of you guys did it with like open circles. And they're just kind of like dotted lines, which I like. Okay, so you probably should label that. As long as you did a good enough job, kind of where it was clear to me what it was going on. So basically this car did not accelerate. Something crazy happened. Then they were accelerating for 3/2 of a meter per second squared. Something crazy happened, and then they accelerated for 0 meters per second the rest of the way. All right, so we're just shy of 40 minutes. That's 2 of the tests. And here's the makeup, and I will start that, I don't know, some other time. Okay. Okay, so it is officially some other time. And let's see. So we're going to start this particular problem. I think so. This slot, this is the makeup. I guess it says that right there. This is the key. Okay, car traveling along a straight flat highway is moving at 41 meters per second. So we've got one car. Let's call that VC. It's, you know, it's an average because it's it doesn't change. Oh, the speeder continues to travel at a steady 41.0 meters per second. So that's V naught of the car. That's V of the car. That's V, you know, it's whatever V you want that to be, because it's not going to change. After a delay of 3 seconds, okay, so how do we, you know, I'm not exactly sure how to write that down. Okay, but there's a 3-second delay, 3-second delay. Okay, and then we have a police car. Let's see, police car is standing on the side of the road, highway. So the police car, the initial velocity of, what do we want to call it? The police car is 0 meters per second. But then the police car is going to accelerate at a steady rate of 5.00 meters per second squared. All right, so what do we want to know? So how long does it take the speeder, the police car, to catch up with the speeder? So we want to know the time, and that time is very specifically the time of the patrol car. Okay, you know, obviously the speeder has a 3-second head start on him, so you know, the difference between the two is going to be 3 seconds. How far does the police car have to travel to catch up with the speeder? So we want to know the delta X for the police car. And how fast is the police car when it catches up to the speeder? So we want to know the V of P, so the final velocity of the patrol car. Okay, so this is one of my favorite problems to think about graphically, which is kind of what I love so much about this particular problem. And let's go over here. And, you know, I'm just going to kind of do this out of the way over here. So here's my, you know, here's my position, X in meters, and here's my time in seconds. One thing that I love about this particular graph is that, you know, things are defined on this graph. So this is X versus time. So X equals X naught plus V naught T plus 1/2 AT squared. Okay, so this particular equation will describe any line that we happen to you know, that we happen to put on this particular graph. Okay, so with that in mind, let's talk about the car. Okay, the car is pretty straightforward. You know, the car is just going at a steady 41 meters per second. Okay, so here's the car. It's the slope of this line, that's the velocity. The velocity is the average velocity in this case, but it doesn't matter which one we want to call it, 41.0 meters per second. Okay, that's for the car. Okay, now the you know, the patrolman, you know, 1, 2, 3, he's going to wait 3 seconds. All right, let's go ahead and get the equation for that line. So the equation for that line is X of the car equals his initial position. Let's call that, you know, where does he start? Well, he's starting at 0, right? 0 plus the velocity of the car times time, okay, for the car. And then this part is 0 because he's not accelerating. Okay, so that is the equation for the car. Okay, so now for the patrolman, on the other hand, let's zoom in a little bit. I don't know why we're zoomed way out. All right, he's going to start at a position that the speeder was at 3 seconds earlier. Okay, and he has an initial velocity of 0, right? So his slope is initially 0. But things are going to, you know, rapidly, he's going to accelerate, right? So his equation here, you know, if we look back up at this equation, it's essentially the exact same idea, right? So the X for the patrolman equals his initial position. So his initial position is, well, it looks like he's at X equals 0. So 0 plus, he has no initial velocity, so we're not going to write that term. And that's going to be 1/2 of A for the patrolman times T for the patrolman. Okay, so that's his equation. Okay, So the temptation here is to plug these into each other, to say, okay, well, I want to know the time when these two cross. I want to know where they cross right here, so I want to know what that time is. Right? But the problem is that this equation is with respect to the time for the patrolman, and this equation is with respect to the time for the car. Right? They don't have the same times. The time for the car, okay, is 3 seconds longer. The car has a 3-second head start, equals TP plus 3. Okay, so, there's a 3-second head start here. No matter where you go in this thing, like if I'm like right here on the line, well, the car's been traveling for 3 extra seconds. Okay, so in other words, I can plug that into here and then solve this equation. Okay, so let me go down here and we can solve that. Okay, so I can say, okay, cool, well, x, c, so I'm going to take this equation right here, I'm just going to bring it down here, equals, I'm not going to bother writing this 0, velocity of the car, TP plus 3, right? It's 3 seconds longer, okay? There is another way to do this, and I think a lot of you would prefer this. It works out to the same thing. This is 3 seconds, right? It works out to the same thing. You could have done this and gone up to here and said, you know what, I'm going to use the same time for everything. They're all just starting at and ending at T, right? But then the car has an initial position, right? So the car has an initial position right here, right? Well, what's that initial position? Well, delta x here, delta x, which is going to give me this initial position, delta x for those first 3 seconds. Well, I was going 41 meters per second for 3 seconds, okay? Notice that's the velocity times the time. Okay, that's exactly what I have here, velocity times the time. Okay, so it works out the same way. If I wanted to plug in 123 right here to give me an initial position of 123, or if I want to just go in here to this equation, and that V naught is going to be 41, and that 3 seconds is going to be 3, and that's going to be 123 there. It works out exactly the same way. So whatever way makes the most sense to you. Okay, so now that they're both at VP, I can put this one down here, and I can say, well, XP equals 1/2 AP TP. Okay, so I'm going to set these two equal to each other, noting that when the X of the car and the X of the patrolman are equal to each other, then that's the time that I'm looking for. Okay, so let's go ahead and do that. So I'll say V bar C times TP plus 3 seconds equals 1/2 AP TP squared, right? Looks like I forgot that squared up there. Forgot it up here as well, it looks like. Okay. All right, so this is going to be a quadratic equation, which is pretty annoying, but it's not the end of the world. Okay, so I'm going to rearrange this before I put values in it. So I'm going to get 1/2 A TP squared. Let's see, so they got that. Now this is going to be moved to the other side, minus V bar C times TP plus V bar C times 3 seconds. Is that a plus? No, it got moved to the other side, so that's a minus. Okay, minus equals 0. Okay, sorry, I did a little, I did distributing and then brought it over to the other side of the equation. Okay, so I'm going to plug in numbers now. Not for any particular reason that this is the time. I just think a lot of you guys are going to prefer doing a quadratic formula with numbers instead of variables. Okay, plus what's in VC is negative 41 meters per second. Okay, and here I'm putting things in parentheses just so that I'll know what A is and what B is and what C is when I do the my calculations, right? So negative 41 meters per second times 3 seconds equals 0. Okay, so this is 2.50 meters per second squared, so that's my A. Plus negative 41 meters per second, that's my B. Plus negative 123 meters, that's my C. Okay, all that is just so I can keep track of what's A, what's B, and what's C. Okay, so now I got TP equals, let's see here, negative B, negative 41 meters per second, plus or minus the square root of B squared, 41 meters per second, squared, minus 4 times A, 2.50 meters per second squared, times C, negative 123 meters. Okay, and hopefully you see that the point of these parentheses and putting is it helps me to not miss any negative signs. Negative 2 times A, 2.50 meters per second squared, right? So here we go, negative B plus or minus B squared. So everywhere where there's a B in this equation, I should have negative 41. Well, I could put the negative there, although it doesn't matter. And then I've got an A right here, and I've got an A right here. Those are both positive, that's good. I've got a C right here, and the only place it shows up is right there. Okay, so I think this looks okay. So we're gonna start with 41 meters per second, plus or minus the square root. Well, let's not do that. We'll use our calculator for that number right there. But we can do the bottom anyway. So the bottom is 5.00 meters per second squared. And on top we get, okay, so we get some number like that. And then it's going to give us two roots, a positive root and a negative root. So the negative root you can see is going to be quite small because 41 minus 54 is going to be relatively small divided by 5. And the positive root, which is going to be fairly large. Okay, so we've got these two times. And if we go back to our thing, so one is a negative time, the other is a positive time. The negative time refers to, okay, so this is time relative to this particular moment right here. So the negative time refers to, if we go backwards, kind of like that. Okay, it has no physical meaning because the police car did not even travel that particular route of that parabola. So we're not really concerned about that, so we'll get rid of that. The positive time is going from here to here. Okay, so that's the time we care about. So over here in our answers, you know, I can say, well, the time of the patrol car, how many sig figs? 3 sig figs. So we'll say it's 19.0 seconds. Okay, so that's the first answer. Okay, cool. So then the second question becomes, I guess if we were to go down here, we would have to make note of that, right? We'd say, well, TP equals 18.991 seconds, and with sig figs, that's 19.0 seconds, 3 sig figs. Okay, so now the next thing we want to know is how far does the patrol car travel? So delta XP, right here. Well, we just need to go find that equation for delta X of the patrol car, which is right here. Okay, we've already done this. So XP, or really delta XP if you really want to get right down to it. But in this case, those are the same. XP and delta XP are the same because X naught is 0, right? The patrol car starts at 0, which is also the beauty of always starting the problems at 0. So X of P, or we'll say delta XP, equals 1/2 AP times TP squared. So delta XP equals 1/2 times 5.00 meters per second times TP squared. Well, the time for the patrol car was 18.991 seconds, and we'll square that. So delta XP equals, so I'm getting 901.65 meters. Okay, so delta XP with the correct sig figs is 902 meters. Okay, or 0.902 kilometers. I don't think it had any requirements that we do this in meters or anything weird like that. So we're going to say delta XP is 902 meters. So a little less than a kilometer, he catches his prey. Okay, VP, a velocity of the patrolman, cannot be solved on this equation unless you know calculus, right? So if you did know calculus, you could, for those of you calculus nerds out there, you could integrate this, but we're not going to be integrating that today. So today for the velocity at the end, we must know that it's going to be V equals V naught, so this is for the patrol car, plus A patrol car TP. Okay, so this is a pretty clean, straightforward. He starts at 0 meters per second, and he's accelerating at 5.00 meters per second, and he does that for 18.991 seconds. Okay, so this is a nice clean one because the calculator can do this for you. And I get 94.9 955 meters per second. So with sig figs, VP is, let's see, so that's 95.0, it looks like, right? 95.0 meters per second. How fast is that? Is that insane? We can do a little conversion here in a second. Okay, so VP final is 95.0 meters per second. Oh, meters per second. So just because we're curious, we could say, well, how fast is that? So it's 95 meters per second times, 10 to the third meters is 1 kilometer times 3,600 seconds is to 1 hour. And I should be more precise in this, but since I'm just kind of going for a ballpark, I've got kilometers. So now I've got, let's see, the meters are gone, seconds are gone. I got kilometers per hour. There are roughly 1.609344 kilometers in a mile. That might be exact. I'm not exactly sure. Anywho, so if we do this math, the velocity of the patrol car is going 212.51 miles per hour. So he's cruising. So he goes from 0 to 212 or 213. I guess it was sig figs 213 in how many seconds? Almost 20 seconds. But he does catch his prey. So that's pretty cool. All right. So anyway, for this one, I'm not going to do this graph because I don't have a copy of that on me right now. And I've already done 2 in this particular file. So that should be enough. Okay. I hope this was helpful. All right. Later, guys. Bye.